All right, the topic for today is vapor pressure. Now, in order to understand vapor pressure, we have to understand what vapor means. Now, a vapor, you might be familiar with the term, is a gas, but more specifically, it's a gas that is normally something else like a liquid or solid at room temperature. It isn't normally a liquid at room temperature, or a gas at room temperature. Oxygen is a gas at room temperature. It's not a vapor. Water is a liquid at room temperature, but you don't have to boil water in order to remove the molecules from liquid into a gas if you add enough heat to it. Which is why when you put a dish of water out for a pet, a dog or cat outside, and they don't touch it, but on a hot summer day, that water disappears. It didn't boil, otherwise everything would be dead. It just absorbed enough heat to allow the liquid to become a gas, and the more heat you have, the more likely that it's going to become a gas when it's normally a liquid. And this is why. Liquid water, which is the most common example we have to understand what vapor is loosely bonded. All liquids are loosely bonded when compared to solids. Solids are the most tightly bonded substances. Liquids are kind of like bonded together but not very strongly, and then gases are not bonded together at all. They're out moving around randomly. So this is kind of like an intermediate phase between solid and gas. So when you pour water, you see the water sliding out of the container. That's pretty much what the molecules are doing there. So when you add heat to this, this causes the molecules to move about faster. Okay? When you add heat to anything, even in solids, doesn't make any difference, gases, whatever, they absorb more energy and they're able to move around. Temperature is a measurement of the energy that the system has. Okay, so if you have loosely bonded molecules like we have with water here, it's going to start moving, and these dotted lines, which I represent here as hydrogen bonds here that we talked about before, they're not as strong as like the hydrogen-oxygen bonds within the molecule, the intramolecular molecule bonds, as opposed to the intermolecular bonds of the hydrogen bond, which are much weaker than that. So when they start vibrating, these things start to become unstable. They'll break apart if you have enough heat added to it, and all the other bonds around to it, because every water molecule has 6 other water molecules bonded to it. And so if you get enough energy, they're all moving about, and also all these bonds are breaking, and one shoots off. That's the vapor coming off. Okay? So if we can actually see, or you don't see it, but you can anticipate that you're going to have H2O gas coming off. And it's not from boiling. It's just the ability to break the bonds, holding it with the other waters. So as you add the heat, the intermolecular bonds break, and the loss of the intermolecular bonds allow molecules to be free and become gases. And that's important. Molecular gases move randomly because they are not bonding to anything. Okay, and so when they collide, they keep moving at the same motion they were before. Now, how does that work? Why do not everything do that? Why, for instance, if I was to take, say, oil and have a plate of oil, a plate of water, put the same amount of heat, let it sit outside, and you'll see the water disappear and the oil does not. Why is that? Well, it's because it depends upon the structure of the molecules and in terms of polarity and in size. Okay? So let's take a look at polar molecules. Polar molecules have strong intermolecular bonds. Remember, we talked about the hydrogen bonds, which are the strongest of the intermolecular bonds, and the dipole-dipole bonds, which are not as strong, but they're stronger than the weakest one. If they are the components that are holding everything together, they're not going to be very likely to give off vapor, gases. Not as likely as nonpolar molecules, which are very weak. Remember, we talked about van der Waals forces. Van der Waals forces are what hold nonpolar molecules together because of the location of electrons being shall we say, uneven throughout the molecule, and you have two consecutive with this uneven shift, and they will be attracted momentarily, and then the electrons, because they're moving so often, move back and they break apart together, back and forth, back and forth. That's how van der Waals forces work. Very weak, or London dispersion forces, more appropriately, what we associate them with it, because van der Waals can be actually involved in more than one thing. Anyway, so it's going to require less heat to break those bonds apart. So, like methane, which is CH4, which is the simplest of the organic compounds, will break apart because they're small and they're nonpolar. If they're large and nonpolar, like a plate of oil, they are not going to break apart very easily because there's so many bonds within the structure. All right, so your vapor pressure is going to be really high, or the number of vapors, I should say, because we haven't talked about pressure yet. But the number of vapors or gases coming off of nonpolar molecules is going to be much higher than they are for polar molecules. Ionic bonds, which is generally what we see in solid structures like table salt and all kinds of different kinds of salts, and these are the strongest of the intermolecular bonds, and therefore it takes a tremendous amount of heat. If you were to take some salt crystals and put it on a frying pan and crank it up as high as it will go, it'll just sit there and look at it and say, well, what am I supposed to do here? It's not going to melt. It's just, now some solids you put on there will melt. You've seen that. Like butter. Butter, well, that's kind of a colloid, but it's solid-like. It's close enough. And when you heat it, you can see it melt, and then you're going to get off vapors from that. That's not the case with ionic bonds. With extremely strong intermolecular bonds, it requires excessive amount of heat. In fact, you want to melt salt, you have to get your stove top to go about 2,000 degrees, and let's hope that never happens. Very few gas will be produced, if any, from that. Okay? Now, let's talk about vapor pressure itself. Pressure is a measurement of the force of collisions with a surface. So like if you ever put your hand over a pot of boiling water, you will literally feel the vapors hitting your hand because there's a lot of vapors coming off all at the same time. And that force at which they're hitting your hand can be measured as a form of pressure by taking the amount of force that they're colliding with your skin with the area of your hand. If you divide those two out, that's technically how pressure is figured out. So lots of gases then, vapors, create high vapor pressure, and like for the ionic compounds and a lot of really strong polar molecules, your vapor pressure is going to be very, very low. So the higher the strength of the intermolecular bond, the lower the vapor pressure. There's an inverse relationship in that respect. Another factor is the size of the molecules. I talked about this, how if you have methane here, this is methane. Methane, this is the Lewis dot structure for it. This is more representative of what you have here. Is remember the 4 bonds here with 4 sets of electrons creates a tetrahedral 109.5 degree, and you basically have your carbon here in the middle, and the hydrogens kind of lumped there, equally spaced apart because the electrons being shared between them. This is very small. You compare that with ethane, which has 2 carbons and all these hydrogens. This is going to have a higher vapor pressure for the methane, and this is called ethane. And this is because you have more London dispersion forces taking place, because it's a larger molecule. This will have a lower vapor pressure. So size matters. Okay?